and statistics lessons. Again, good evening and welcome to you from all over the world. If you are watching this live stream, welcome to GER Hub Mathematics and Statistics lesson. I remain Dr. John Effiong Hussein, your mathematics teacher, your statistics teacher, and of course, your research project writing teacher. If you are watching this video live from any part of the world, please do well to smash a like on this video. Endeavor to subscribe to the channel if you haven't subscribed to the channel, and make sure you turn on your notification button, as it will make you get notified on videos we drop or when we go live. Thank you very much for your support, your continuous support to our channel. Please do well to keep supporting the channel as it makes us grow. Thank you very much. That being said, in today's video, we are going to be looking at another episode on the second part of functions of a real variable. Now, for you to go back to the very first video we made on functions of a real variable, I would like you to click on the link in the description below. That will take you to the video. Okay, so what will be the objective of this video? So let's quickly write out our objectives. So what will be the objectives of this study? Okay, so the first thing we must take note of is that we are still on functions of a real variable. Okay, so this remains our topic. So in the first instance, we considered in our first class on functions of a real variable, we had considered what the definition of a mapping is. So in that class, we talked about a mapping, and we defined a mapping to be a rule of association that associates an element, a unique element in Y, in two sets. Okay, let's assume that there are two sets, A and B, such that one is called the domain and the other one is called the codomain. So what we call a mapping is a rule of correspondence or a rule of association that assigns a unique element from the codomain to an element in the domain. Again, a mapping is a rule of correspondence or association that assigns a unique element in a set called the codomain to elements in a set called the domain. Okay, so we discussed that in the last class and rounded up that class with discussing functions. So what will be the aim of today's class? In today's class, being the second part, episode 1 of this same topic, functions of a real variable, we shall be considering three major objectives. So we shall explain what a function is. So we shall explain the meaning of a function. So we shall explain what a function is. 2, in this same class, we shall explain one other way of representing a mapping. Okay, so this other method of representing a mapping is called the method of ordered pairs. So we are going to look at this also, ordered pair explanation of mappings. Then 3, and finally, we shall be looking at types of mappings, and we shall be considering in this video 2 major types. Okay, so types of mappings. So once again, welcome. Let us now focus on the very first objective. The very first objective is to explain what a function is. So I'm going to take this. So the question is, what is a function? If you followed the video on the first class, you will recall that I told you that a function is a mapping whose codomain is necessarily the set of numbers. Okay, so when the codomain necessarily is the set of numbers in a mapping, that kind of mapping is called a function. Again, a function is a mapping whose codomain is necessarily the set of numbers. Now, if you go online to look at other materials, they won't be wrong to tell you that a function is a mapping whose domain and codomains are the set of numbers. It's still not a wrong definition, okay? So, necessarily, out of the two sets, the codomain must be a or the set of numbers, okay? So a function is a mapping whose codomain is necessarily the set of numbers. Now let us go into explaining using concrete examples what a function is and what a function is not, okay? That will give you a clear example on what this definition is all about. So let's see. Now let's assume that there are two mappings. So I'm going to put a mapping here, A mapping on A being my domain, and another set, the codomain B. Okay, so let's define our mapping to be F on this set A and the set B. So the set A I'm taking to be my domain. I'm taking the set A to be my domain, and I'm taking the set B to be my codomain. Okay? Now, when can we say F, this mapping, is a function? Let's consider putting elements 1, 2, 3, and 4 in A. And let's consider putting elements 7, 9, 11, and 13 in B. Okay? Now, if I assign the element 1 a unique element from B, 7, and I assign the element 2 a unique element from the codomain 9, and I do the same thing for 11, assigning an element 11 from the codomain to an element 3 from the domain, and I do that also assigning 13 a unique element in B to 4, an element in the codomain. Now, the question is this: is this mapping a function? Again, what is our definition of functions? Our definition of function says a function is a mapping whose codomain is necessarily the set of numbers. But what I'm trying to explain here is that the definition goes a little bit beyond what we have just defined. Meaning that for this function in particular to be a mapping, not only must the numbers in the codomain not only must the elements in the codomain be the set of numbers, but you would notice that every element in the codomain is a unique assignment to elements in the domain. Now, what is the clear relationship of this mapping or of this function in particular? Now, for us to look at this, most times in certain exams or tests, you may be asked to develop the relationship existing between the elements of the codomain and the elements of the domain. Now, this is clearly a typical example of a function. Why? The elements of the codomain assigned to elements in the domain are numbers. Okay? Hence the definition that a function is a mapping whose codomain is necessarily the set of numbers. So, what is the relationship F? So, what is the relationship F? Okay? Now, if you remember or you've gone through the video on mappings, or the first video we made on functions of a real variable, you will recall that there were three major notations for describing a mapping. So if I want to describe this mapping, which is a function, I could say f a into b. This will be one way of describing this mapping. If I don't want to use this, I could use the notation f a b. I could use this notation. Or I could pick a random element from the codomain x under this function and equate it to y. So these are three possible notations for the mapping. Now let's use any of them or one of them, okay, to explain what is going on here. You would notice that there is a relationship between the elements in the codomain 7, 9, 11, 13 and the elements in the domain 1, 2, 3, and 4. Now, notice this, that for you to get an element in the codomain, all you have to do is to multiply the element in the domain by 2 and then add 5 to your result. Again, to get an element in this codomain, all you have to do is to multiply an element you pick from the domain and add 5. Multiply an element you pick from the domain by 2 and then add 5 to your result. So let's see. Notice that 2 times 1 plus 5 would give us 7. And notice again that 2 times 2, that is multiplying this element by 2 and then adding 5, will give us 4 plus 5, which is 9. Notice again that multiplying 2 with 3, this element, and adding 5 to your result will give you 2 times 3 is 6 plus 5, 11. And then finally, multiplying this element 4 by 2 gives 8. Adding 5 to it gives 13. Now, if you pick a general element, let's say we use small letter x to represent any random element from this, from this domain. Let's pick a random element x. If you pick a random element x from this domain and multiply it by 2, add the result to 5, it will give us a value y. And what is the value y? The value y is f of x. It is a function of an element in the domain. So what it means is that this mapping f is indeed a function. Again, why is it a function? It is a function because the elements in the codomain are necessarily numbers. So mappings could become functions only when the elements in the domain and codomain are numbers. But the codomain must have elements that are necessarily numbers. Let's take another example. The same way you could have this, one could ask you to define a mapping. F of x equals 2 times 2x plus 6. Okay? So, where x contains elements 4 and 5. Now, in this case, it means I could pick a set A having elements x, 4 and 5, and I will define a mapping F from A to B, another set B. Now, what we want to do in this case is to determine what the elements in B would be. What would the elements in B be? The elements in B will be generated using this. 2 times an element in A will give you 2 times an element in A plus 6 will give you an element in B. So 2 times 4 will give you 8. 8 plus 6 is 14. That means 4 is mapped into this set, giving 14. And 2 times an element 5 in A plus 6 will give us a result here. So 2 times 5 is 10, and 10 plus 6 is 16. So you are going to have 16. And that will be a function. So For functions, take note, a function is a mapping whose codomain is necessarily the set of numbers. That being said, let us go straight to taking the next objective. So, for the next objective, we shall be looking at a notation for mappings, another notation for mappings. So, one other way for representing mappings is the use of what we call ordered pairs. Okay, so we've seen that mappings could be represented in this manner, mappings could be represented in this manner, and mappings could be represented in this manner. Okay, so remember also that you could use any letter to represent your mapping. What is the mapping? The mapping is simply a rule that assigns an element in a first set, say A, the domain, a unique element from another set, a second set, say B, the codomain. Okay, so when a mapping now has its codomain as the set of numbers, that mapping becomes a function. Now we do this. So you just in case you are not clear on when a relation is a mapping, let me use this medium to explain to you what circumstances, under what circumstances a mapping, a relation is said to be a mapping, and under what circumstances a relation is said not to be a mapping. Okay, so not every relation is a mapping. Now, under certain circumstances, a relation may be a mapping, and under certain circumstances, a relation may not be a mapping. So, let's see. We want to answer the question before we move into our second objective. When is a relation a mapping? So, there are two conditions I'm going to give. One, if a relation is a mapping, so every element in the domain of the mapping must have an image. If every element in the domain do not have an image, then that relation is not a mapping. Let me give you an instance. Okay, so let's say we pick two sets A and B. Okay, and there are A, B, and C elements in A, and we have here G, H, I. Now, if I assign to A in the element A in A, the element G in B, okay, under F, for instance, we are considering at this moment F to be a relation, and we want to answer the question, is F, this relation, a mapping? Now, for us to know whether F is a mapping, we must examine condition A. Every element in the domain of the relation must have an image. Now, if there is at least one element not having an image, then that relation is not a mapping. So, I'm going to assign A in A, an element G in B, and I'm going to assign B in A, an element I in B. Okay, so I'm going to do this. Now, I'm going to also assign okay, I'm going to just stop at this point. A has been assigned G from B. B has been assigned I from B. Now, the question is this. Is this particular relation F a mapping? The answer is a big no. And why is that so? There is an element C in A that has no image. And the condition says for a relation to be a mapping, every element in A, the code and the domain must have images in B. Now you will notice that C has no image. Now H has not been assigned any element in the domain A. and that does not matter. So not every element of B, the codomain, must be an image to an element in A, but every element in A, the domain, must have an image in B. So for the singular reason that C, an element in A, the domain, has no image in the codomain, this relation F is a mere relation. It is not a mapping. So I would simply say this relation, the relation F, is not a mapping. And why is that so? Why is that so? It is because C, an element of A, has no image in B. Okay? So C, an element of A, has no image in B. For that reason, F is simply a relation. It is not a mapping. Now, let's go to the second condition, B. Now, what is the second condition? The second condition is that every image in the codomain, must be unique. Every image in the codomain must be unique. Now, for an image to be unique, what does that mean? For an image to be unique, it simply means that, let me put up another example. Now, for an image to be unique, it means that two images cannot be assigned to one element in the domain. Okay? So, two images cannot be assigned to one element in the domain. Okay? So, for an image to be unique, note, two or more images cannot be assigned to one element in the domain. Okay? So, in that case, what do we have here for this mapping? So let's take a relation H defined on two sets A and B, and let's take the elements, let's say X, Y, and Z, and let's put here A, B, and C. Now, I could have this, and I could also have this. Let me introduce another element D. So if I have an element D in B and an element small b in B, now such that these two images are assigned to A, immediately you have two or more images assigned to one element in the domain. This kind of relation H is not a mapping. Why? It destroys or disobeys the uniqueness property of the images of the codomain. What is the uniqueness property of the images of the codomain? The uniqueness property states that every element in the codomain must have must be uniquely assigned to elements in the domain, meaning that no more than one image cannot be assigned to one element in the domain. Okay? So that is what the uniqueness property is all about. So is this relation a mapping? The answer is a big no. It is not a mapping because the elements in the codomain, these images B and D in the codomain, have been assigned to one element in the domain. So that means this relation is not it is simply a relation but not a function. That being said, let us now go to the next thing I want to explain. And what is the next thing I want to explain? I want to explain our second objective. The second objective of this class, remember, was to explain what other way there is to describing a mapping. Okay? So, and I'm saying that a mapping can be described also as a set of ordered pairs. This is very simple to understand, so let me show you. So let's assume that we have A to B, okay? So we have two sets A and B with a mapping defined on them. And let's assume that we have A, B, C here assigned to E, F, G. Okay? So, what are we trying to say? A mapping, this mapping F can be represented as an ordered pair. And what is an ordered pair? In an ordered pair, we have elements in the domain coming first before elements in the codomain to which they've been assigned. So you would have for this mapping F to be an ordered pair. Okay, so F can be written as A, E in brackets, comma, B, F in brackets, and C, G in brackets. So when you do this, or when you use this for representing a mapping, what are you using? You are using an ordered pair to represent this mapping. Okay, so you'll be using an ordered pair to represent this mapping, and that's why I'm saying that ordered pair explanation of mapping is essential for you to understand that you can actually use ordered pairs to explain a mapping. Okay, so look at it again. This is the mapping F. If I give you an expression like this or a diagram like this, clearly depicting that F is a mapping from A, the domain, into B, then you can use an ordered pair to explain this mapping by simply writing F equals a set containing every element in A with their respective images, with the elements in A coming first before the images in a bracket. So this bracket that contains elements in A first before elements in B to which they've been assigned is called an ordered pair. So mappings can be represented with ordered pairs. Let me give another example. So what if we had a mapping H defined on a set C and D? Okay, let's assume we had this. I had X, Y, Z, B, and I had here F, G, H, C. So I had this, I had this, I had this, and I had this. Now, this is a mapping. Why is it a mapping? Every element in the domain has an image in the codomain, and the uniqueness property is satisfied because there are no two elements in the codomain that have one image or one element to which they are assigned in the domain. So this is clearly a mapping. Now, if you want to represent this mapping with an ordered pair, you end up having the mapping H. You write it out and equate it, taking in brackets every element in C, in this case X, and their respective images. So I'm going to take X and F. I'm going to take Y and G. I'm going to take another bracket containing Z and G, and I'm going to take another bracket containing B and H. Now remember, not every element in the codomain must be an image to an element in the domain. So irrespective of the fact that C has no element to which it is assigned in the domain, this is still a mapping. Remember, for a function, for a relation to be a mapping, it means that every element in the domain must have images in the codomain. Okay, and the images in the codomain must be unique. Now, that being said, you can look at it again to understand what we've just explained on ordered pairs. Now, in today's class, I'm going to end my class with the last objective. So what is the last objective? It is to discuss types of mappings. So let us quickly go into discussing types of mappings. Now, there are basically three types of mappings I'm going to be discussing, but in this particular video, I'm going to take two of them. Okay, so I'm going to take the two of them out of the three. The first type of mapping that we are going to be discussing. Okay, let's start with listing them out. So the first one is what we call the one-to-one mapping. Okay, so the one-to-one mapping is the first type of mapping. Two, we have the onto mapping. Onto mapping. Now this one-to-one mapping is usually called an injective mapping. So if you don't want to call it a one-to-one mapping, you could call it an injective mapping. Then the third type of mapping is called a bijective mapping. Okay, so I'm going to save my discussion on this for another episode. Okay, but in this video I'm going to discuss one-to-one mapping, otherwise called the injective mapping, and the onto mapping. But that does not mean I'm not going to tell you something about the bijective mapping. I'm going to explain this just a little bit, okay? But we shall save our discussion for the next episode on this particular topic. So let's start with one-to-one mappings. So what is a one-to-one mapping? So for us to define a one-to-one mapping, let X from into Y under F be the mapping. Let F of X into Y be the mapping that that establishes the correspondence between the sets X and Y, with X being the domain and Y being the codomain. Now, the question is this: if this is the mapping defined from set X into Y, then when can we say F, the mapping, is a one-to-one mapping? So we are going to say then the mapping F is called a one-to-one mapping. Is called a one-to-one mapping if different elements in the domain, that is X, have different images in the codomain. So if every element in the domain has different images in the codomain, that kind of mapping is called a one-to-one mapping. Now, what does that mean? Let me show you this. Example of a one-to-one mapping is a mapping like this. So let F be a mapping from A to B, such that A is my domain and B is my codomain. If I have X, Y, Z here, and I have A, B, C, such that X is assigned to A, Y is assigned to B, or B is assigned to Y, A is assigned to X, and C, an image, is assigned to Z, then you will notice that every element in A has an image in B, and the images are different. So X has its own image in B, Y has its own image in B, which is B, small b, and Z has its own image C in B. Every element of the domain has a different image in the codomain. This kind of mapping is called a one-to-one mapping. Again, what are one-to-one mappings? They are mappings in which you have different elements of the domain having different images in the codomain. So what does that mean mathematically? So we could say alternatively, if F X into Y is a mapping, that is, if F of X into Y is a one-to-one mapping, then F of X1 will be equal to F of X2 implies that x1 is equal to x2. Or if f of x1 is not equal to f of x2, then x1 is not equal to x2. So this is just another way algebraically of explaining what we have just defined. What this means is that if I pick an element here, if I pick any two elements here such that they give me the same image, then it means that those two elements are the same. If I pick any two elements here that give me different images, then those two elements are not the same. That's what we are explaining here algebraically. But what you should know is that when a mapping is 1-to-1, that mapping has every element in the domain assigned different unique images in the codomain. So that being said, let us go to the next type of mapping that I'm going to be discussing in this video. So the next and last type of mapping I'm going to be discussing in this video, saving the bijective mapping for a later date, is the onto mapping. So when is a mapping onto? When is a mapping onto? So we are going to say that is onto mapping. When is a mapping onto? So just like we did earlier on, let f of x into y be a mapping from domain x into codomain y. We would say the mapping f is onto if every element of the codomain, is an image of at least one element in the domain. Okay? So if a mapping is an onto mapping, the first thing you must know is that every element in the codomain of that mapping must be an image to at least one element in the domain. What it means is that this kind of mapping that I'm putting up here is not onto. So if I have a mapping A, B, and C, and I have here D, E, and F, such that this is assigned to D is assigned to A, E is assigned to B, and the same E is assigned to C. This is a mapping, okay? So this is a mapping, but this mapping here is not onto. Why is it not onto? You will notice that F, an image in an element in B, is not an image of any element in A. So for a relation to be a mapping and that mapping to be an onto mapping, then every element in this codomain must be an image to at least an element in the domain. But because F, an element in the codomain, is not an image to an element here in the domain, this mapping is not onto. So remember, for a mapping to be an onto mapping, every element in the codomain must be an image to at least one element in the domain. So let's give an example of an onto mapping. Let's give an example of an onto mapping. So let's assume that we have H. Yeah, this is A, B, C, and D. And let's have E, F, G. So if I have E assigned to A, F assigned to B, and I have F also assigned to C, and I have this. This mapping is an onto mapping. Why is it an onto mapping? It is an onto mapping because every element in the codomain, while satisfying the uniqueness property, is an image to at least one element in the codomain. You will notice that F, an image in the codomain, is an image of B and C, at least one element, that is one or more. So F is an image to B, it is also an image to C. Okay, so if every element in your codomain is an image of at least one element in the domain, then what do we say about such a mapping? That kind of mapping is an onto mapping. Now I'm going to end this class with telling you a little bit about a bijective mapping. Sometimes a mapping can be both one-to-one and also onto. When a mapping is one-to-one and also onto, that kind of mapping is said to be a bijective mapping. So we are going to start our discussion in the next episode on functions of a real variable with that particular statement. Thank you for watching this video, staying tuned to this channel live. I am grateful to that one person I can see clearly on my channel. Thank you to every student of CRUTECH watching this video, especially the year 1 students and those from mathematics and statistics department. Okay, thank you very much for watching this video. I will see you in my next class. Please smash a like on the video, subscribe to the channel, and turn on your notification button. I will see you in my next class. Thank you very much.